So opposite is positive or negative. Reciprocal of sine is cosecant. Reciprocal of cosine is secant. And now we're doing the inverse. So two different ways you can notate the inverse. You can write out the word arc sine or arc cosine, or you can have it raised to the -1. Now, it is very important that you notice the -1 is to the sine and the cosine. It's not to the x. We could raise x to the -1, and that's a completely different problem. Now it's just a regular sine or cosine problem. Okay, so be sure that -1 is in the correct place. Now, this says remember that inverse sine and inverse cosine are inverse. We can't remember that yet because we don't know that yet. That's going to be Unit 3. But Unit 3 will have to do with this kind of stuff. In Unit 3, we're going to evaluate. So there's some things in Unit 3 that are going to make a lot of sense when you get there because of graphing. These two units could really be flip-flopped. There's good and bad for doing each one first. But I think there's more good in doing the graphing first. So there's a couple things we're just going to say, know this. And then in Unit 3, it'll make sense why we know that. So just some things that you know about inverses from Algebra 1 and or for sure Algebra 2. Analytically and graphically are two ways that you can find the inverse. Analytically, you switch the x and y's and solve for y. So if I were to say y equals 3x plus 2, find the inverse, we would say x equals 3y plus 2, and then you solve for y. That's how you did that. Or the same thing with parabolas, square root functions, irrational functions, all of those different things. We can't do that yet with sine and cosine. We don't know enough information about that yet. So we are going to do the graphing. Graphically, it's a reflection over the line y equals x, which means you switch the x's and the y's. When you switch the x's and the y's, the graph becomes a reflection over the line y equals x. Y equals x is just a line that goes through 0, 0 and has a slope of 1. All right? We are graphing functions. They have to pass the vertical line test. Not all of them do that. Think about a parabola. If a parabola faces up and we switch all the x's and y's, now it turns on its side, so we have to have some restrictions. If you were going from a square root function to a parabola, you had to list restrictions. You were only looking at the parabola to either to the left or the right of the vertex. So the same thing's going to happen today. Because when we have a sine graph, so if you print it in color, terrific. If not, if you didn't print in color, it's not a big deal. We just put the color one on there so you could see it. The red line is what we've been doing, the sine function. If we were to switch all those x's and y's, it becomes the blue function, which we can look at and tell it is a reflection over the line y equals x. But think about this point right here. Let's say this point right here. So this is 0 and almost 3. So almost 3, 0. So we just switch those points. This is -1, a little bit bigger than 4. So 4, a little bit smaller than -1. So you can see we flip-flopped all those points. That blue graph is not a function. It does not pass the vertical line test. I put a vertical line test. It passes through more than once. So we have to restrict the domain. Now, there's lots of sections we could take to restrict, but we're going to pick one section because we're going to give you a graph every time that has the pi's and pi over 2's on it. So if you pick some other one, you're going to have to come up with your own graph, which is fine, okay? But I would suggest using the nice little graph that we give you because it's all labeled on there for you, okay? We will always give you the graph with the pi's and pi over 2's on them when we expect you to do anything with the arc sine and arc cosine. All right, so if we look at that red graph, that next little page you have there, that's the sine function. We are going to pick a section of the graph that will make its inverse a function. Bless you. You might have done the horizontal line test. If you put a horizontal line down on a function, that will tell you whether its inverse is a function or not. So if we just look at that whole red graph, it does not pass the horizontal line test. Therefore, its function is not an inverse. So that's why we have to restrict the domain. And we are going to pick -pi over 2 to pi over 2 as our restriction. Now, could we pick pi over 2 to 3 pi over 2? Yes. Could we pick -pi over 2 to -3 pi over 2? Yes. There's tons of little sections we could pick to make it a function. But We want to include 0. So I want to include 0, so that's what we're going to use. That is the domain we're restricting the sine function to, so that its inverse is a function, because we need to draw functions. So what's going to be important are these 3 points right here. Those 3 points on the sine graph, we're going to switch the x's and the y's and becomes the arc sine graph. So if we just pick that little section right there. So that next picture is just that little section. So the section that's in white right there, this is that section right there. So we picked negative pi over 2 to pi over 2 because that makes its inverse a function. So if I think about the regular sine graph, if I plug in negative pi over 2, I get negative 1. Goes back to the unit circle. Here's negative pi over 2, here's 0, here's pi over 2. Y is equal to 0 down here. I'm sorry, negative 1 down here. Y is equal to 0 and y is equal to 1. So those are nice points. Now, those other points are on there to show you why we don't pick all the points. If I picked pi over 4, that's fine, but the sine of pi over 4 is 1 over root 2, or root 2 over 2, which most of us don't just know what root 2 divided by 2 is off the top of our head. So that's why we pick those nice quadrantal points. Same reason why we have those 5 critical values that are the high, middles, and lows. With arc sine and arc cosine, we pick 3 values. So here is the sine function, and notice if I plug in negative pi over 2, I get negative 1. For the arc sine, I flip those. X and y flip-flop. Plug in 0, I get 0. Flip-flop stays the same. Negative pi over 2, 1. The inverse of that is 1 pi over 2. So these 3 points in blue, this point right here, this point right here, and right here, those are the 3 points that you should memorize. Then we're going to move them left and right, up and down, reflect over the x-axis. We can do all those things with those 3 points. Now this domain down here is just to show you that if we take the domain of the function, it becomes the range of the inverse. The range of the function becomes the domain of the inverse. And notice there are not arrows. We are not continuing on the graph. If we put arrows or make the graph continue, then it's wrong because it's no longer a function. If I just wanted to continue this graph a little bit more, now it's no longer a function. So now it's not right. If I wanted to put an arrow on it, now it's not right. It's not a function anymore. That's not correct. If I graphed it the wrong way, let's say I went this way, is that the same graph? Are those 2 blue lines the same? No, they're not the same. So the concavity is very important. Start at the top dot, come down, and go through the middle, and get to that bottom one. Concavity is very important because that's going to be right or wrong. If your concavity is wrong, then it's a completely different graph. We don't even have any of the points here the same. All these points between 0 and negative 1, between 0 and positive 1 are all wrong. Okay, so the concavity is very important on those. Think that next page on your notes looks like this. It has the arc sine and the arc cosine right next to each other. All right, so those are the parent functions. We need to know these points right here. So the arc sine, we have the point negative 1, negative pi over 2, 0, 0. We just did this, and 1 pi over 2. If we can't remember those, then think about sine. You've got to remember the restriction, though. Plug the restricted numbers into the sine, and then flip-flop the x and the y, if you have a hard time memorizing those 3 points. For arc cosine, our restricted domain is going to be 0 to pi, because that's what section we could take out of the parent function of cosine to make its inverse a function. So that would be the point 1, 0, 0 pi over 2, and negative 1 pi. So those 3 points for each of those graphs are the kind of parent function points that you would shift. Now, there are points in between, but again, they aren't nice numbers, so we could find them, but we don't have a calculator, so most of them we couldn't even come up with without a calculator, and this is all non-calculator so far. All right, so the examples here. Graph the following functions in radians. Arcsine and arccosine will always be in radians. We're going to give you this little graph. This will always be provided for you if we expect you to do anything with arcsine and arccosine as far as graphing goes. So the first thing says state the transformation. Well, this one only has one transformation, and that transformation is right 3. Remember, transformations go in PEMDAS order. Parentheses, exponents, there are no exponents, multiply, which would be reflect over the x-axis, and then add and subtract, which would move it up and down. All right, so the way I like to do these is I like to plot the parent function points. So it's arc cosine. So I just memorized my arc cosine points. 1, 0, 0 pi over 2, and negative 1 pi. Now, notice there is a pi hash, and then there is a 3. 3 does not equal pi. 3 is very close to pi, but pi is a little bit bigger than 3. Pi is 3.14. So don't put your dot on the line. Put it right above the line where the pi is. Okay, it is not the same. And 3 is not in the same place as pi. This is a coordinate plane. Each line is 1, 2, 3. Then there's a pi with a little slash mark right there. That's where pi is. Pi is not on the line. So be careful when you're drawing it that you do not plot your high point right here at 3. All right, so now what I do, and you don't have to do this, okay? I just think it's easy to plot those points and then move them to the right 3. Mosquito. So here, 1, 2, 3, plot that point. 1, 2, 3, plot it. 1, 2, 3, plot it. And now we can graph our function. Again, the concavity is important. I always start at the top dot and come down and come through, and then your concavity is correct. Start at the top point, come down and go through. The next thing, state the domain and the range. So the domain would be the x values, which would be 2 to 4. Both are included. Notice I didn't go above or below either of those points. I came to a stopping point at the high and the low, or the left and the right. And then the range is the low value up to the high value, which is pi. It is not 3, it is pi. 0 was my lowest value, pi was my highest value. Now, this next one is not on your notes. What I did is I took that same problem and I put a negative out in front of it. Okay, so again, it's not on your notes, but what if we put a negative? If we put a negative out in front, we would still move right 3 first, then we would reflect over the x-axis. Don't just say reflect. Reflect over what? We are reflecting over the x-axis. In that order. When you're listing your transformations, they must be listed in order. So again, we plot our 3 parent function points, and I'm going to move that right 1, 2, 3, and then I'm going to reflect it over the x-axis. So if I'm at positive pi, reflect over the negative x or the x-axis, takes me to negative pi, correct. And I move to the right 3. I'm at pi over 2, so that's going to take me down to negative pi over 2. Right 3, I'm at 0. I don't go anywhere. So I start here, down and go through. So there would be my transformed graph. Again, not on your notes, but just something that could happen if there's a negative out in front. Things get reflected. All right, this one, our only transformation is up 2, but it's arc sine. So arc sine is negative 1, negative pi over 2, 0, 0, 1 pi over 2. Move those points up 2. Now, I'm at pi over 2. Is pi over 2 plus 2 equal to pi? It is not. Okay? It is equal to pi over 2 plus 2. So I don't know exactly what number that is, but I know that pi over 2 is about halfway between 1 and 2. So I can move that up 2 units. Up 1 would be about halfway between 2 and 3. Up 2 would be about halfway between 3 and 4. So there's my up 2. 0 gets moved up 2, goes straight to 2. Negative pi over 2, up 1 unit, up another unit. So we end up about halfway between 0 and 1. And then we start at this top and go down and through. I think he's fighting me. And there's your graph. So for our domain and range, our domain is easy. -1 to +1. Left to right. The range is a little more difficult on this one. We still have a low point, but how do we know what that is? We can't just like guess and say, oh, I bet it's about a half. Okay, we can't do that. That's not correct. We have to look at where we were and how far we went. We were at negative pi over 2, and we moved up 2. So we added 2 to negative pi over 2. So that's what you write. Negative pi over 2 plus 2. That's the low value.
Why can't you just... Oh, wait.
Get a common denominator?
Yeah,
You could, but then you still end up with a pi because they're not like terms.
Right.
So earlier we got a common denominator, and that's fine, but then you still end up with a pi because you still can't add pi to a number right here. Okay, so that's just extra work that's not necessary. And then our high value, again, we don't know exactly where that is, but we know we started at pi over 2 and we added 2. So pi over 2 plus 2. And that is your range. So if you don't know, you have to go to where you did know. We knew for sure we were at pi over 2, and we added 2 to get to that, or added 3, or subtracted 4, whatever it might be. You take where you started. You're never going to start at the same place for the high and low value, but you're always going to do the same thing to it. So this was moved it up or down. Range moves up and down the y values. Domain is affected by what moves it left and right. And then I did the same thing for this one. If I made that negative, in this case, we would have to reflect over the x-axis first and then move up 2. Now, this one matters, what order I do this in. Because let's just take this point right here. So we have our 3 parent function points. If I reflect this over the x-axis, so I go down to negative pi over 2, and then up 2, that's where I end up. But if I had done that out of order and moved this up 2 and then reflected, I end up down here. So notice that order is very important. Okay? PEMDAS. Always follow that order of operations when doing your transformations. Left or right. This parentheses is left or right. This will be reflect over the x-axis. This will be up and down. Very important to do that. Yes?